online. So you can do that Adobe Research in Paris, right? And we have Pascal Grittmann as the academic mentor. So maybe not everybody knows the procedure. So Alexander will first present his results, and there will be a discussion with examiners, and then also the public audience will ask questions, and then the committee will use the requirement and decide about the conclusion. Okay, please, the stage is yours.
Then, thank you very much, and welcome to my defense on the topic of how to train your render. As you probably all know, computer-generated imagery is more ubiquitous than ever before. It allows us to preview architectural marvels before breaking ground. It allows us to practice complex surgeries without a living subject and explore alien worlds from the comforts of our homes. A key challenge in generating these images is that renders start out very noisy, and it can take hours or potentially even days or weeks of computation before noise levels become acceptable. So in this talk, I will show you how we can use clever mathematics to drastically reduce the noise in our renders, which means that you only have to wait a fraction of the time to reach your desired noise levels. We will begin by looking at the mathematical foundation of the problem we're trying to solve with rendering, namely light transport simulation. Spoiler, it's really all about computing integrals. Naturally, that means we'll have to understand how contemporary approaches compute these integrals using Monte Carlo integration. During this part, you'll also see why noise is such a big problem. Combating this noise is possible in various ways. We will look at two of the fundamental approaches that employ learning to reduce noise in our simulation. We'll begin with my research on path guiding, namely variance-aware path guiding, as well as focal path guiding. We will then move on to my research in Russian roulette and splitting, namely EAS, efficiency-aware Russian roulette and splitting, before then concluding the talk. But without further ado, let's jump straight into it. The goal of rendering is simple. Given the description of a virtual scene consisting of geometry, material descriptions, light sources, as well as a virtual camera, we want to produce a photorealistic image, as if the scene was captured by an actual camera. Ergo, we need to compute the color of each pixel in our image. This problem is known as light transport simulation, where transport is just a fancy term that describes both the propagation of light as well as how it interacts with objects. To compute our pixels, we just need to find and evaluate all the possible paths that light could take throughout our scene. Like this one, for instance, or this one. Really just all of these. Put mathematically, we can compute each pixel IPX as an integral, where the domain of integration is the set of all light paths, and the integrand is the measurement function f that takes a given path x bar and tells us how much light it carries to our camera. This measurement function is a product of multiple terms, such as the amount of light emitted by the light source, then how much of that light arrives at the next vertex of our path, the so-called geometry term that, for example, takes care of the inverse square law. And then there's also the BSDF that determines how strongly the material reflects light from one vertex to the next. And these terms repeat until we arrive at the camera eventually. Here, the camera response function WPX tells us how sensitive the pixel PX is to the light coming from the previous vertex. Note that all of these terms are fairly straightforward to compute, so we will consider this the easy part. But let us still talk a bit more about the BSDF, however. This function is particularly interesting because it determines how objects look. So far to say, there's a lot of exciting research on this function. But for our goals today, it's sufficient to know the basic shapes. For example, a smooth distribution will reflect light in all directions equally, resulting in a diffuse look. Whereas a more peaky distribution will result in glossy appearances, like this one. And finally, in the extreme case, light is only reflected in a single direction, creating a specular material that looks like a mirror. In reality, materials are often much more complex, as they mix and match various more intricate shapes. But for now, let's move on to the next topic. This topic I want to start off by telling a little tale about an ominous creature I coined Miniacs. Now, Mini-Alex here has recently been trying to compute the area of the circle. Unfortunately, he never went to school, and so he never learned what pi is. And he has been kind of stuck on this problem for a while. So in a tantrum, he decides to start throwing darts at the circle. Suffice to say, Mini-Alex is not very good at playing darts. All the darts he's throwing are just uniformly distributed over the board. He is good at counting things, however. And as he counts the number of darts that land in the circle, he notices a very peculiar pattern. For some reason, the ratio of darts that land within the circle seems to converge to some value as he throws more and more darts. Even if he starts over, the ratio keeps converging to the same value every single time. Imagine Mini-Alex's amazement as he realizes that this very number happens to be precisely the area that he has been searching for all this time. Mathematically, Mini-Alex has computed an integral problem, where the domain of integration is the dartboard, so the green area, and the integrand is the indicator function of the circle. So it's 1 for points within the circle and 0 for points outside. But how did he do this? Well, he did this by generating a random set of samples S, evaluating the integrand for each of them, and then averaging the result. And to get the scale right, he also multiplied by the size of the domain, in our case, the dartboard. Mini-Alex soon realizes that he can compute any integral this way. He just needs to pick random points in the domain, evaluate the function for each one of them, and then just average their results. And the result will magically converge to the integral value. Congratulations, Mini-Alex. We have just rediscovered Monte Carlo integration. There's two very important properties I want you to take away from this. First, we can use this to estimate integrals of any shape and dimension. All we need is a way to pick random elements in the domain and evaluate the integrand. But second, because of the stochastic nature of this approach, our results will be noisy. Different runs will give us different results early on. Luckily, since this process converges to the true value of the integral, we can just reduce the noise by taking a sufficient amount of samples. Unsurprisingly, Mini-Alex starts applying Monte Carlo integration to all the integrals he ever wanted to compute. But he soon makes a devastating discovery. For mostly flat functions, everything works perfectly and he gets very accurate results even with only a few samples. But whenever he tries functions with higher fluctuations, he needs a huge amount of samples to avoid noisy results. In yet another tantrum, Mini-Alex throws the integrand in his hydraulic press. Where did Mini-Alex get the security clearance for such a dangerous device? I have no idea. But the device is surely doing a great job at flattening the function. Amazing. Unsurprisingly, when we apply Monte Carlo integration to the now fairly flat function, it indeed has way less noise. And quite amazingly, it also still converges to the same integral value. So, what has happened here? If we look at the grid of our function plot, we realize that the area under the curve stayed the same. It has merely shifted around a bit. The x-axis was stretched in a couple of places, like this one for instance, and in other places it was compressed, like here for instance. But wherever it was stretched, the y-axis is squeezed by an opposing amount. Weird. And here it's stretched. So this keeps the overall area the same. Mathematically, what we have done here is called a change of variables. We've replaced our domain with a warped version of the domain. When we apply Monte Carlo integration to it, we are warping our uniform samples into a new distribution that is no longer uniform. And to cancel out the stretching of the domain, we divide the integral f by how strong the stretching of our warping is, which is known as the probability density of the new distribution. This approach is known as importance sampling, and it is the foundation of everything that I'm about to show you today. The key takeaway here is we want to find sampling distributions that reduce the noise in our estimate by closely resembling the shape of our integral, as this reduces the number of samples we need to take and hence the time we need to wait for our computer to finish. Okay, now let's tie everything we've learned so far together. Remember how I said that light transport is just a fancy integration problem? Well, that means we'll use Monte Carlo integration to compute it. All we need is two ingredients. First, we need to evaluate the integrand, that is, determining the energy of the light path with the measurement equation. This part we have already seen is fairly straightforward, and we'll consider it a solved problem for the remainder of the talk. All we need now is a method to sample the domain, that is, to generate light paths somehow. And this is what we'll be focusing on throughout the remainder of the talk. By far, the most popular approach to constructing paths is path tracing. It begins with rays at the camera, then intersects them with the scene, and at each intersection continues the path in a new random direction, rinsing and repeating until we reach a light source eventually. This algorithm is simple enough that it can fit on business cards, yet powerful enough that it can render entire movies. Most of what we discuss in the following will be based on this very algorithm. Now, given the stochastic nature of the Monte Carlo integration, we will of course have noise in our images. How strong the noise is depends on how strongly our measurement function fluctuates. Glossy materials, for instance, or small light sources, or narrow gaps in objects can all introduce peaks in the measurement function that manifest themselves as noise in our renders. It is therefore crucial to employ importance sampling when constructing our paths. In path tracing, the usual strategy for picking the next direction is sampling according to the material response. This means we send more rays in directions that are reflected more strongly, which helps reduce the noise introduced by glossy materials. Let's see how this changes our image. Hope you can see it. Might be a bit closer. Okay. It's also possible to connect to points directly sampled on the light sources, a process known as next event estimation that reduces noise in direct light from small light sources. Nice. Over the years, researchers have proposed countless such sampling strategies that can reduce the noise of individual light phenomena. However, implementing more sophisticated techniques is often a tedious undertaking, and there are many effects that are not handled well by any existing technique yet. A popular alternative is to react to unforeseen events by employing learning techniques that adapt to the effects automatically. For example, using a technique known as path guiding. Let me start with an example scene. In this scene, we have a challenging lighting. There's a lot of indirect light from a small, brightly illuminated spot on the scene. Path tracing is unlikely to explore these regions, and hence there would be a lot of noise in our image. Path guiding addresses this issue by building distributions from samples that we have seen previously, and then steering later samples towards these promising regions. Put simply, our algorithm is learning which directions to sample as we are rendering. There's a couple of ingredients to make this possible. First of all, we will need some kind of model for the distribution that we are learning. We call this the representation of our guiding algorithm. A common strategy is to recursively subdivide the scene using a spatial tree structure, and then let each of these leaf nodes learn their own independent directional distribution. We call the composition of such spatial and directional structures spatial directional guiding structures. Next up, we'll also need some training speed. Guiding is usually performed in iterations, so each of which samples a couple of paths per pixel and then uses that information to update the guiding structure. We'll also need some kind of mapping from the samples that we have seen to the distribution that we want to fit our model. Both of these ingredients, the representation as well as the fitting process, are important design decisions of a guiding algorithm. As existing works mostly rely on heuristics for that, but in the following, I will introduce you to two of my papers that strive to optimize these for more explicit goals. Quite fittingly, we'll begin with the fitting aspect. An important question, independent of the choice of representation, is which target distribution to strive for. In other words, given some input samples like this here, what should our distribution look like? Most works follow the same basic heuristic, but to understand it, we'll have to massage the path integrated formulation. Let's say that we have already sampled the first two vertices of our path. Hence, we can move those out of the integral. And because we sampled them, we also have to divide by the respective probability density as we've learned earlier. We will call all the terms that have been sampled already the throughput, which we denote as T. The throughput tells us, if we were to hit a light source at the next vertex, how strongly this light will contribute to our image. Next up, let's split the integral into sampling the next vertex, x2, and all the other vertices that follow. We'll call this subintegral Li, which stands for the incident light, as it tells us how much light we are receiving at the current hit point from whatever direction we go in next. And lastly, we'll also perform a small change of variables that changes our integration over path vertices to an equivalent integral over directions. This change of variable cancels a lot of factors in the geometry term, leaving only a single cosine. The result of all of this is a localized view of the path integral, which happens to be known by the name of rendering function. For practical reasons, most renderers consider the cosine term a part of the BCF, which we'll also do in the following for conciseness. When it comes to sampling this integral, we would ideally like guiding to learn the entire integral. This is known as product sampling because it samples the product of incoming light and material reflectors. So if the green distribution here is our BCF and the yellow one our incident light, then the blue distribution is what we would like to sample. Unfortunately, this is quite challenging because the blue distribution has a lot of dependencies. It depends on the current hit point, the direction we came from, and the direction we go in next, making it a 7-dimensional distribution. Instead, existing works opt to only learn the incident light, which has no dependency on the direction we came from, and hence is much easier to learn. The hope is that by alternating between BSDF and guiding samples, we're handling all terms of this integrand well. And this works well if the BSDF is diffuse or if the incident light is diffuse. But if both of them have peaks, then the resulting distribution can be very different from what we want to sample. So what we've asked ourselves is the question, under the same constraints, so given a 5-dimensional representation, can we find a better target function that we should learn instead of pure incident light? The way we tackled this question is by formulating our search as an optimization problem. The underlying goal is to derive a target that will minimize the noise in our render for some error metric. I'll spare you the details of the derivation, but for the popular relative mean square error metric, optimal distribution is this one. Okay, I know it looks a bit daunting at first, but fundamentally, it's still based around using incident light as a distribution, just with a few additional factors that we'll explore one by one in the following. First up, note that these angular brackets here mean that we're using a random estimate of the incident light, and the fancy E is the expectation operator. It tells us what a random value will converge to if we take more and more samples. So this part of the density is still equivalent to incident light. Let us begin by looking at this wonderful diffuse floor, which is illuminated by the sun, as well as the reflection of the sun in a glass pane. Sampling according to incident light will send most samples directly towards the sun, and only few towards its relatively dim reflection in the glass pane. But this is problematic, because paths that reach the glass pane undergo another random decision, namely whether to reflect or refract, which is not usually guided and thus introduces a lot of noise. By substituting incident light with what's known as the second moment thereof, our density prioritizes directions that would otherwise cause a lot of outliers. Let us now look at a glossy scene with multiple light sources. Here, existing densities struggle because they should race towards light sources that are not actually reflected by the material. By incorporating the average reflectance, our density mitigates this problem. This achieves some of the benefits that product sampling would have, while still sticking to our 5-dimensional representation. And here's a scene that shows another problem of previous guiding densities. Because each directional distribution is responsible for a large region of space, we can have situations in which a distribution is responsible for both the front side of an object, like this door for instance, as well as its back side. Obviously, these require very different sampling decisions, creating a conflict in our distribution. The throughput term in our density weights all directions by how impactful they are to the image, and therefore handles these conflicts more gracefully. A similar conflict can also occur on glossy objects. Here, we focus most rays on the light source, which minimizes the absolute error of the image, but sacrifices darker regions in the process, because they matter less for an absolute error net. Dividing by how bright the pixel is results in a more balanced distribution that optimizes the more visually appealing relative error metric instead. To evaluate our density, we have implemented it in practical path guiding. Despite all of the extra factors, our distribution requires less code than previous densities. We've evaluated its performance on a large set of 22 test scenes and have found that it often halves the noise at equal render times, especially for renders longer than a minute. Here is an example scene, namely from the glossy kitchen scene, in which we greatly reduce noise over previous state-of-the-art guiding. Equal render time. And here are the results for the necklace scene, in which our method is the only one to realize the importance of guiding rays towards the diamonds that create intricate acoustic patterns on the table. We've also applied our theory to some related problems, like how often to pick each light source in next event estimation, as well as optimizing the ratio of how often to sample the VSF versus how often to sample the guiding system. We also show that our method can improve methods that perform analytical products, like the practical product path guiding. You can find many more evaluations in our paper. But for now, let's shift our focus to another important aspect of guiding algorithms, namely the representation that is used to express the sampling distribution. To illustrate an important fundamental issue of spatial directional guiding representations, have a look at this wonderful camera obscura scene. Here, light from the outside enters a darkened room through a minuscule hole in the wall, creating a projection of the statue on a canvas. Despite its conceptual simplicity, this scene is a nightmare to render, even for state-of-the-art path guiding algorithms. The problem is that the pinhole is so small that only a few of our spatial regions actually manage to construct paths that cross it, while all the others miss it entirely. In the following, we show how to overcome these limitations by using a global distribution instead of individual local ones. But the camera obscura scene is not the only case in which a continuum of paths all need to pass through the same region in space. We've coined this family of effects focal effects, and in the following, I'll show you the different kinds of focal effects that you might encounter in your life. The simplest focal effects occur directly at our camera or at our light source. Paths converge here because they either start or end in their location. Accordingly, we will call these direct focal points. These are the simplest to handle because their location is known upfront. More interesting are indirect focal points, in which light interactions with objects create focal points. For example, when we point a laser at a wall, or when light needs to pass a narrow gap, such as this open window. These are much harder to handle as the location is typically not known upfront. Finally, there's also virtual images of focal points, which happen when the perceived location of a focal point is shifted through refraction or through reflection. The location is also usually not known beforehand. Some of these focal effects are handled well by existing techniques. Path tracing, for example, begins past the camera, and hence it systematically explores the camera focal point as well as all the virtual images thereof. And with next event estimation, we also explore light focal points. There's even fancy variants of next event estimation that have some support for reflections of light sources. It's also possible to run path tracing in reverse, starting at light sources instead of at the camera. This technique is appropriately called light tracing, and it captures light focal points as well as their virtual images. A powerful strategy is to combine path tracing and light tracing, which gives rise to so-called bidirectional techniques. For example, we can connect camera subpaths like this one and light subpaths at each vertex. While bidirectional techniques are very powerful, they are also very tedious to implement, which is why most renderers stick to plain path tracing. And as we'll see later, they also still struggle to sample certain focal points. Our solution to handle this family of effects robustly is to replace the spatial direction scheme commonly deployed in guiding with a purely spatial distribution that captures where in space paths need to pass through. We represent this distribution through a spatial tree structure. And to learn the distribution, we just split the energy of each path that we trace into all the regions encountered along the way. Since focal effects mandate that all paths pass through the same regional space, these will end up having the most energy in our data structure. And to pinpoint the exact region that paths need to pass through, we increase the resolution of our spatial tree structure in high energy regions, but we have also derived a scheme to prune regions that only subsets of paths pass through. Sampling our distribution is simple and clean. We only have to import a sample at a point in space according to our spatial density, for which we can use hierarchical sample walk. We then continue our random walk in a direction pointing towards our central focal. This way we systematically construct paths to explore focal regions. But that's enough boring details. Let's have a look at some fancy renders, starting with the camera obscura scene from earlier. Pinholes are a particularly challenging focal effect that is not handled well by any existing. Even bidirectional methods fail to find paths that explore the projection of the scene. Our guiding successfully identifies the location and extent of the focal region and robustly incorporates it into path construction. Our version of the dining room scene shows another challenging focal effect. Parabolic lampshades produce virtual images of small light bulbs. Here, bidirectional methods benefit massively from starting rays at the light sources. Despite its lack of light tracing, our method successfully samples this focal effect and converges significantly faster than the existing state-of-the-art path guiding. However, our approach performs poorly for non-focal light transport, such as this living room scene. Hence, we believe the best use of our method will be to augment rather than replace existing methods. So, now that you are all experts on guiding, let us turn to another fundamental technique that allows us to shape our path distributions to our liking. Remember, our fundamental goal is to avoid paths that have different contributions, as this results in noise in our image. Guiding tries to avoid this by changing the directions that we continue our path. But there's another way to shape our path distributions, which is based on at each intersection randomly deciding whether we want to continue the path or terminate it instead. And this technique is fittingly known as Russian roulette. For example, paths bouncing over brighter surfaces could have a higher chance to continue, while paths that have already lost a lot of energy have higher odds for termination. Similar to importance sampling, we reduce the probability of generating samples with lower contribution. While this additional random decision can increase the noise in our image, applying it selectively can significantly reduce compute time with only minimal increase in noise. And the key difference to guiding is that guiding tries to prevent these paths up front, whereas Russian roulette is reactive in nature. This can be a strength, because even with guiding, we will have many paths that end up contributing little to the image. Especially as paths grow longer, they tend to lose energy as they bounce around the scene. At the same time, Russian roulette has a direct influence on the compute time of the image, which allows us to do trade-offs that we cannot do with guiding. In practice, it is therefore recommendable to always use both guiding and Russian roulette. Okay, now that we are deciding whether to continue the path with one sample or 0 samples, a natural question is, could we also take more than one sample at each intersection? The resulting technique is known as splitting, and the goal is to reduce noise from high contributing paths by averaging multiple estimates for the remainder of the path. Of course, this will increase the computational cost, but if we selectively split the right set of paths, a significant reduction in noise will outweigh the hopefully minuscule increase in render time. So, for a given path prefix, how do we know whether we want to apply Russian roulette or splitting, and by how much? Let us begin by briefly revisiting existing approaches. We'll begin with the most common approach to Russian roulette, which is known as throughput-based Russian roulette. This technique looks at the product of the throughput and the BCF that we have just sampled to determine with what chance to terminate the path. For example, this floor here reflects 90% of light, and hence would have a 90% chance of survival. The darker wall, however, would have a higher chance of termination. Despite its simplicity, this method works extremely well in practice, because the resulting distribution of paths follows the energy that paths retain while bouncing around us. It has one fundamental flaw, however, in that it is unaware of the incident illumination. For example, at both of these points here, the floor reflects the same amount of light. But the left one is actually in shadow. Hence, continuing a path here will result in lower contribution on average. Adjoint-driven Gaussian pattern splitting addresses this by learning an estimate of the incident light at each point in space, which estimates the contribution of the complete path rather than the treatments. This solves the shadow problem, but still overlooks an important aspect. Even when 2 points are equally brightly illuminated, it can be beneficial to treat them differently for 2 reasons. One is cost. If we know that one of the points will need many bounces to reach a light source, then Russian roulette can be a good idea to save a lot of compute time. The other factor is noise. If we know that the remainder of the path creates a lot of noise in the image, then it might be a good idea to split it. Similar to variance-aware path guiding, we approach this problem as a mathematical optimization problem. This time, however, it's not sufficient to minimize noise alone. We must also take into account how our decisions affect the computational cost of our render. To this end, we optimize an important metric known as efficiency. Formally, efficiency is the inverse product of cost and variance. This metric measures the speed at which our renderer is converging. Note that this approach isn't entirely new. Prior works has tried to optimize a very similar problem formulation, but quickly found that an analytical solution is infeasible and hence resorted to simplifying the problem. Unfortunately, this simplification degrades the quality of the Russian roulette and splitting decisions, and hence the resulting equations, are impractical to implement. So instead, we have found a practical numerical solution to this optimization problem based on the concept of fixed points. Now, what's a fixed point scheme, you wonder? Well, I'm glad you asked. Let's say I asked you to solve this equation. You'll quickly notice that there is no analytical solution because of the complex nonlinear dependency of x on itself. By the way, this is what the right-hand side of the equation looks like, and the left-hand side is just diagonal. Our goal is to find the intersection, as that's where the 2 sides are equal and the equation is solved. Just for fun, let's do the following. Let's pick a random x. We can get on the blue line just by evaluating the expression. Now look what happens when we use the result as our new x. We are now magically closer to the solution. And when we repeat this a couple of times, we get closer and closer to the solution with every step. And I assure you, this is not a fluke. If we started elsewhere and applied the same scheme, we would also magically converge to the solution with every step. What we have just done here is known as fixed point scheme. All we are doing is running a function on its own output, and it metrically solves itself, as long as a couple of conditions. In our paper, we have derived a fixed point scheme to find optimal Russian roulette and splitting decisions. That means you can start with any arbitrary guess for these decisions, for example, using a simple throughput-based scheme that we discussed earlier, and then by repeatedly applying our equations, you get closer and closer to the optimal decisions. This fixed point scheme is surprisingly simple to implement and also efficient, because we only need to learn a couple of additional statistics. Representation-wise, we can just piggyback on whatever data structure you already have at hand, for example, from guiding. In our paper, we also proved that all the necessary criteria are fulfilled to make this a valid fixed point scheme. In particular, that it converges to something, which also happens to be an extremum of the problem, and that extremum also happens to be the global optimum of our original problem. Intuitively, our scheme performs a low splitting where the variance at the current hit point is high compared to the average variance in the image. And at the same time, it avoids splitting where the local cost is high compared to the average cost in the image. We've evaluated our method on a large corpus of 19 test states and found that on average it achieves 50% higher efficiency than the previous state of the art, while remaining just simple and practical to implement. Here is a scene that nicely illustrates why it's insufficient to only consider how bright this region is illuminated, because this results in too little splitting being performed underneath the table. our method is aware that this region is responsible for most of the noise in the image, and hence performs much more aggressive splitting, resulting in an overall 4 times faster convergence than the scene. So while we were at it, we also used the opportunity to apply this efficiency optimizing fixed point scheme to a couple of other problems. For instance, multiple importance sampling. Also have Joshua right here in the audience. The nice thing about this approach is that it achieves even higher performance than these, by being just as simple to implement. But the even nicer thing is that it allows us to produce some very psychedelic looking renders, like this one. Here, we have encoded the number of samples of each technique, the first hit point for a bidirectional path tracer. More red means more VSF samples, green corresponds to next event estimation, and blue is connections to line paths. On the right walls, you can see that our technique automatically avoids next event estimation on the walls, as this region is in shadow. Apart from that, we've also applied these fixed point schemes to neural path guiding, which we will probably soon be able to read about, hopefully. Here, we converge twice as fast as the state-of-the-art path guiding. But more on that another day. For now, let's conclude by revisiting what we have learned today. The ways that light interacts with our world are numerous and fascinating. While specialized techniques exist for certain types of light effects, handling unforeseen ones requires adaptability through learning methods. In this work, we explored what constitutes effective learning algorithms for light transport, from data representations and the targets to be learned to the fitting process itself. And by strategically optimizing these components for desirable goals, such as overall render efficiency, we have demonstrated significant improvements over approaches that rely on heuristics. Now, there's numerous other decisions in light transport that are still based on heuristics and would benefit from learning. We hope that the insights gained by my thesis might inspire others to look at learning from a new perspective, with an emphasis on goal-driven optimization of the individual components of learning algorithms. But that's for another. With that, thank you for your attention, and I'm happy to take questions.
So you could start with the online,
Yeah.
right? So Rami, would you like to start with your questions?
Sure. Thank you. I hope you can hear me well. Thank you, Alex, for this presentation. It was extremely clear, just such as the document that I really enjoyed reading. Congrats on the document. That was really nice for me to read, because I learned a lot of things, and I love when I learn things. So thank you.
It's
very,
very
very useful.
Thank you very much.
I have a couple of questions. A few technicals, nothing too difficult, and a few about the opening toward future work. Maybe the main question I have is regarding what you ultimately learn in all your work. So, in path guiding, you try to learn something about how light traverses the scene, reflects, and so on. Most of your models are basically scene dependent, right? One question I have would be, how can some of the contribution you made can be, how some of the learning you're actually making can actually be shared within the scene and among scenes, going toward, a form of learning that would go beyond the current image that you're trying to learn. Did you look into that? Did you think about how contributions can be used there?
Yeah, first of all, that is a super exciting area, I think, of research, and one that needs a lot of work. Because there's, maybe as just like a forward, there's one thing that I've always been wondering with guiding in the first place, and that is, what is the amount of information that we can extract from the samples that we have seen anyway? Because this is a very fundamental theoretical question, right? Because we don't know currently how much there's still to be gained. People are hand-tuning their representations and stuff, and we don't know if we've already approached the ceiling or if we could do much better. So I think what we need is, first of all, some theoretical foundation for knowing really how much we can learn and extract from samples we have seen previously. And then the part going beyond the single scene, I find that also super interesting because, we then know what is the limit we can extract from a single scene, but there's a lot of phenomena that will be similar across scenes. And maybe there's this one glass in this scene that also was in another scene, and it was maybe illuminated similarly, and maybe you have a similar caustic, and yes, you should be able to benefit from that, but that means you will have to have some model that somehow doesn't just learn the current scene, but also learns data from other scenes. And that way we could go beyond this limit, and I've always kind of dreamt of going beyond this limit, but I haven't come up with an idea yet. I know that there are some works that try to approach this, for instance, as like a denoising problem. We are saying, hey, we're learning guiding distribution, and we have seen and we've trained a denoising model on a lot of other guiding distributions from other scenes that we've seen earlier, and then denoising it and hoping that that will make the distribution more accurate. And I don't remember what exactly the results were there. I think it had some benefit. I mean, it was published, but beyond
that,
that,
think that
it doesn't mean
the very representation of the scene would be able to that end. Like we do a lot of, self-similarity factorization in 3D modeling and the appearance modeling. On the appearance model, the geometry, the light. If you look at the most advanced scene representations, they fold the scene so many times through instancing, through local reconstruction from many textures that are reused everywhere in the scene. There is this notion of sharing data within the models of the scene, and all the distributions that you construct, could they be part of this factorization process? Somehow moving those distributions from the very ephemeral state in which they are used in rendering to something that is actually fully part of the scene description.
That is actually a super interesting idea. I think one of the main challenges will be to somehow, because it is, yes, it is dependent on the geometry, and if you're doing instancing and you have the same geometry in a couple of places, that is one part of the light transport that you could kind of try to reuse, but given that it's a product of also the incident light, and you have to factor in the context in which the object is to make these decisions on where you want to go, that actually makes it very challenging. And I don't think reusing some geometric information alone will be sufficient to benefit guiding, because it's maybe more about the context and the light field than just the geometry. You could benefit maybe if there's a couple of glasses on a table, for instance, and they throw similar caustics, because that could work. The lighting conditions are similar enough that you could transfer them, but then you would also have to detect that, like detect the similarity, maybe using the fact that the instance could already give you a hint to that there might be similarity, but you still have to.
I don't think that the sharing would be intuitive to a human. It's not like sharing light transfer properties between two regions that look the same and would have similar lighting conditions. It's probably more subtle. I recall when I was working on fast guiding that we were able to share some information in the direction space, some information in the positional space, and ultimately the guiding process would pick up information from both to build a local distribution whenever we need it. So I don't know, it's an open question, I don't have an answer in this space, but I believe that there is a lot of redundancy in the generation of all these distributions.
There's two works that also come to mind in that regard, and that is neural path guiding methods, which in theory, like the neural model could identify these similarities across the scene and reuse them, but it's a bit hard to introspect whether they are doing it. And also, there's always these kinds of trade-offs that people are doing with these neural models, where they're still relying oftentimes on spatial structures like hash grids and so on to do the heavy lifting, and then you're kind of hindering a network potentially also to do more global optimizations that could benefit from different things. And the second thing actually I want to mention is from my research on radar simulation, I'm aware that in radar, a lot of times people will actually pre-compute light transport, more the reflection characteristics of objects, and then do essentially like an object level rendering, where they're not really simulating rays, so to say, that bounce around objects. They're really treating these objects like points, like point masses, something like that. So maybe in a sense, one could also pre-compute a certain light effect phenomena for certain objects. If you know certain light comes in, then a certain caustic maybe comes out. So that could also be an interesting avenue.
If I may chime in at that point, Tammy, can you relate that to the NVDH paper? I mean, to some degree, that's what we're doing, right? We're subdividing the scene, we're pre-computing transport, storing about, but then we're still doing the light transport because it is a global operation.
Yes, but the optimization is entirely focused on the geometry. And for the geometry, it makes a lot of sense. You can reuse that for instancing, or you can compress it a lot with NVDH. The problem is, and we haven't tried with light transport yet. I know that Phil had some ideas. He always wanted to try that, especially with caustics. And I think it could be interesting, but it boils down to the same problems I mentioned earlier, that it is very heavily dependent on where the object is. So, and also the other problem I mentioned earlier, that piggybacking on like a spatial structure makes you really good at localized phenomena, but not so good at global phenomena, which can take a lot of time to converge. Yeah. Yep.
Yeah.
Sorry,
Tommy.
Tommy.
To NVDH maybe could be established by increasing slightly the dimensionality of NVDH. You know, if you start to have your reflectance properties and maybe some additional geometric information as additional dimension to the space in which the NVDH lives, maybe there is some hope here. Maybe also the dictionary-based solutions. Like if you in your distributions using a dictionary that you optimize for a while actually generating the distributions, then you do some sharing of information in the way the atoms of your dictionary are built, basically. And ultimately, it's a little bit like finding kind of an optimal set of basis functions for your distributions that could be shared within, but maybe amongst it. I don't want to spend too much time on this, but I'm curious too.
There's the paper I also want to mention in that regard. Not sure if you were hinting at that. There's this paper that extended hash grids, so multi-resolution hash grids, with these cookbooks, where they're essentially learning like a dictionary, like you kind of coined it, a dictionary of certain things, and they're using that as like a color palette, so to say, of the raw hash grid. And I think they also demonstrated some benefits in terms of compression, and maybe also that could help the network kind of identify similarities, because then it will notice, hey, my dictionary has these similar entries here, and maybe it should merge them. Oh, right, we also have an expert on splitting and merging here. So he could look into merging these cookbooks for neural representation.
I don't know how much time I have for questions, so I will just keep going and stop me whenever it's too much.
I'm here all day.
A practical and technical question, like in mass guiding, usually you would not assume that much about the way the scene is represented. It's a set of triangles, and then you have some PSDF available each time you hit a triangle with a ray. Assuming that your scene is actually made of parametrized surfaces. Triangle meshes coming with a proper UV parametrization, and all the appearances are actually spatially varying the LDFs that are stored as textures with many maps at your disposal. Is there any way to use the specificities of this particular representation to improve on the distribution estimation each time you hit one? In particular, if you have at your disposal this UV space, can you use it as an efficient cache for computing and interpolating the distributions?
Okay, yeah, there's a couple of points here. Using the UV space for kind of like surface-bound guiding in a sense, I think that is similar, if I'm not mistaken, to how the point clouds work in Gilles Rober's online learning of parametric mixture models. So I think they were already using kind of like a surface-bound structure, not necessarily based on the UV parameterization, but at least based on surfaces. Regarding UV parameterization, I haven't seen anyone do that. And there's one thing I would potentially be worried about. Namely, like the hope is that your UV unwrapping is also good. Like it corresponds to it corresponds well or correlates well with spatial position. Because if there's tiers, it might actually create problems, because then you think these might be similar because they're similar in UV space, but they are maybe not similar. So you might confuse your model this way. And actually, I wouldn't say that there's no assumptions that we make in path guiding. There's maybe one very strong assumption that I think pretty much every guiding algorithm does, and that is that we assume that light transport is sufficiently similar locally. Like that if you have one point that you've learned a sample here, that you can use that knowledge at a nearby point. And that's a very important point, and that's why I'm also pointing out that your UV space should then ideally correlate with space so that you're actually benefiting from this. Because most of the time, this assumption works pretty well. There's not a lot of discontinuities in a light field, especially for indirect light, unless you have hard shadow edges and so on. But oftentimes it will be very smooth in many cases. Sufficiently smooth that we can assume that it's, unless it isn't. And then we need something like, for instance, parallax compensation and stuff. But that's also another. Oh, and another thing I forgot to mention. Regarding whether we can use surface parameters, that's actually an interesting thing a lot of neural models do. They don't use the UV space, but they use the different textures, so roughness, anisotropy maybe, and all of the different things you could have for your materials, and then use these to inform the guiding design. Because sometimes these can also correlate with space, but also most importantly, because a lot of times people will try to learn product distributions, especially with neural approaches, and there it's very important to know these things, like the roughness at a certain point, and certain other things you might want to learn, not directly the guiding distribution itself, maybe the mixing ratio between BCF and guiding should also ideally depend on the roughness, for instance, because depending on how rough you are, you want to do more guiding or not. If you're only making this dependent on like the position in space, then your model is very uninformed and will have a hard time learning the right decisions.
Just as a disclaimer, I did most of my work on global illumination in the space of UV-less representation, so point-based stuff. So, but at the same time, I'm seeing in production how beneficial it is to use whatever you have at your disposal, like both the UV parameterization and the textures that are made available to you in production rendering, I think are underused today. And I totally understand your point about being wrongly informed about some similarities that should not exist because the UV parameterization is telling so. But at the same time, I think that in many cases, you can detect that. And you can decide whether you use it or not, based on both the 3D geometry and the UV parameterization. So what I meant was that using textures and UVs, you might actually have a way to, share within and among the scene content by leveraging this so much easier space, which is the UV space, in which finding self-similarities between texture maps is so much easier than doing that in 3D.
Okay.
One other question I had, maybe to open a little bit the discussion is, 5 years ago, Monte Carlo methods were introduced to geometry processing. Since then, a lot of papers and research has been conducted moving away from finite elements and using Monte Carlo integrations for geometry processing problems. So, first of all, did you look a bit in these fields, Monte Carlo geometry processing, and second, do you think that some of your findings might actually be useful there, or at large, is path guiding, for instance, in general, something that could be translated from path tracing to work on sphere, because in this field, path tracing is replaced by another very simple business card size algorithm called work on sphere, which happens to be surprisingly effective.
Yeah. So first of all, I'm unfortunately very unaware of what is going on in geometry processing. I have heard about all the walk on spheres talks. I've seen that they're super popular and there's a lot of things on these at conferences, but I'm not really into the topic. I do know, however, that for related problems, so there's also been other branches of research that have also started to employ more Monte Carlo techniques, and those also usually see a lot of benefits. We've also done this for radar simulation, for instance. We've done a lot of Monte Carlo radar simulation at the chair, and we've seen that we can transfer these techniques. like path guiding, for instance, with here and there a few tweaks because the problems might be slightly different, but the underlying techniques are still so fundamentally similar that you can transfer a lot of stuff. And also Russian roulette and guiding, I think, or in general adaptive importance sampling, I think are two techniques that you can almost always apply to problems. And there's also, well, no, that I don't know if it's published, but there's some other interesting stuff here. There's also going to Monte Carlo or even other stuff. I think all of these have in common that you can apply these principles.
Yeah, well, if you find time, I suggest you just have a quick look at Monte Carlo Judgment. Because I do think that there are many low-hanging fruits there. You certainly have an eye while detecting where you work with the be used.
Ömercan also wanted to do, there's now Monte Carlo fluid simulation, and the idea was to also apply something instead. So that's also something I've heard, fluid simulation. Cool.
Well, with that concludes my questions. Thank you very much, Alex, and I'll pass the mic to the next jury member.
Okay, so I go next. I mean, first of all, congratulations on strong thesis, also very well written and illustrated thesis, and also thanks on your presentation. I enjoyed the details. I mean, the window goes open and the window closes again.
It's a lot of fun to animate. It takes way too much time, it's a lot.
So you enjoy what you're doing, and that shows in all aspects.
Thank you.
So I'll go through the various sections. I have some questions on each. Variance aware path guiding. So basically, throughout the approach, you optimize local decisions in isolation.
Yes, mostly.
And in the conclusion, sort of, you write the phrase, I mean, that in all the examples, doing more and more of these local optimizations improves the results, but then you write, there is, however, no strict proof that the isolated decisions will converge to an optimal joint distribution. Do you believe that this theorem holds? Or couldn't you, don't you think on the opposite, that you could construct a worst case example? And sort of my question is, if you wanted to construct a counterexample, how would you go about constructing this?
Okay, so I have to first think about it. It's been a while since there is a path guiding. So what was stated that like a locally optimized joint, locally optimized distributions will not converge to, or not necessarily yield a globally optimal distribution.
There is no strict proof that the isolated decisions will converge to an optimal joint distribution.
So let me think. Trying to say. I mean, one thing it's definitely clear if you have a distribution that is that has less parameters than your problem. Like when we invariance with path guiding, it's 5-dimensional, and there is definitely the case that even if you optimize this for the 5-dimensional case, you're still marginalizing over some dependencies. So you're not always doing the optimal thing. If you have a full distribution at your disposal, so one that has all of the dependencies, 7-dimensional ideally, then if you optimize that, and it's perfectly proportional to the integrand, then actually it should be optimal, at least in the sense that if you're optimizing something like variance of your image, so you're not looking at the computational cost, it's another can of worms, you're looking just at the variance, then if each of the decisions, starting at the camera even, and at each bounce, should just through base theory actually yield an optimal distribution. So I'm not sure if I'm maybe missing some context or I forgot what we were trying to say back in the day.
Yeah, I was thinking that maybe if you come up with some strange scenario.
I can come up with strange scenarios for that the 5-dimensional distribution where it will fail.
I mean, yes, I think you need that sort of some kind of an answer that sort of you need the full space.
Yeah,
Prove some. I mean, in order to prove something, you definitely need full space.
Yeah, definitely. There's a thing.
I mean, might be worthwhile. I don't know, you know this, but try to improve it.
I think, yeah, I think the proof should be possible as long as your information, like as long as the distribution has sufficient parameters, and that means you can look at the problem either as, and there's path guiding works that look at it, at sampling entire paths essentially at once, but you can also, if you look at it from an incremental perspective, like path tracing, and at each point you do the optimal thing, starting at the camera and then also starting at, and then at each bounce you have 700 distribution, and it's all optimal, then you can actually achieve any distribution, or you should be able to achieve any distribution you want, and that should be able to perfectly match the product of all these things, like the conditional densities, to give you a density, like a full density for the entire path, that should be optimal. But there's one thing I wonder right now, namely the length of paths could, because it's, could that be a problem? I think there's some theoretical nuances that need to be ironed out.
We don't have to do this on the fly now. I think sort of 5-dimensional make this problem 5-dimensional will probably solve them. Thanks.